new topic. So by, what's the next test is, I think next Friday. I think it's 2 weeks from today, something like that. But this will be on that test. And then we'll probably just do a little bit of substitution and elimination. I'm not sure how much of that I want to do since y'all covered it pretty good deal in part 1. So we'll figure that out when we get to it. But today, we're going to start talking about the applications of alcoholides. I'm abbreviating alcoholides. All right. So we talked about how to make them, right? We talked about being able to make them from using allylic bromination. We talked about being able to make them from adding HX to an alkene, from converting alcohols into alcoholides. So now let's talk about some uses of alcoholides. And one of the major uses is what we call the synthesis of organometallics. Let me write that out all the way. Right, synthesis of organometallics. That's one of the major uses of alcoholides. All right. So what is an organometallic? Right, the name is kind of some indicative of what you're talking about. You have an organic part and you have a metal part, right? So organometallic. What it really is a compound. I'm just going to write out a simple one here. Right, that has a covalent bond between carbon and a metal. Right, we're going to talk about 2 different types of organic, well, really 3, but one of them is only in passing. We're going to really talk about like really 3 different types of organometallics. One of the things about the organometallic, again, it's a actual covalent bond. It's not ionic, but you can think about it like this. You can think about it like the carbon being negative, get these electrons right, and then the metal being positive. Right? You can think about it that way. But that's not how it is in real life. In real life, there's actually a covalent bond between those 2. All right. So in the organometallic mostly acts as a nucleophile. Right, it's nucleophilic, and carbon is obviously the nucleophile because it's, if you break it apart, carbon ends up with a negative charge. The reason the carbon is nucleophilic is because the dipole here is towards carbon. Right, so carbon is partially negative, and then magnesium is partially positive, or whatever the metal is going to be partially positive. All right, so it's nucleophilic and carbon is the nucleophile. So one of the uses of organometallics is what we call coupling reactions. Right, so we use it for coupling reactions. I'm going to talk about all of that later. We're actually going to talk about that tomorrow. All right, any questions so far?
Used for coupling reactions?
Coupling reactions. We're going to talk about it. I'll give you a generic example now, but we'll talk about it more tomorrow once I send out send the videos out for that.
And you said carbon's gonna be nucleophilic.
Carbon is nucleophile. So the electrons in that covalent bond, when that organometallic, excuse me, reacts, it's going to react with some electrophile. I'm just going to go ahead and show you two examples, and then I'm going to talk about the different types of organometallics and how to make them.
Is it always between a carbon in the middle?
Yes.
Okay.
Yep. Good question. All right, so it's used for coupling reactions, and then we're also going to talk about carbonyl additions. All right, so carbonyl addition, coupling reactions, those are the two major reactions that we use organometallics. So both of them are very important. When you talk about, I know we were talking about stereochemistry, I was showing you a bunch of different drugs and things like that. All of those drugs, like sometimes those carbon-carbon bonds that are really difficult to make, they make those using organometallic coupling reactions. So we'll talk more about that. But let me show you an example of a coupling reaction. And then I'm going to show you an example of a carbonyl addition. And then we're going to talk about the different types of organometallics. All right. And if I'm going to save these notes. So if anybody is panicking by not getting a chance to write everything down, I'm recording the lecture and I'll save the notes and I'll post them to Blackboard. So let me switch colors right quick. So an example of a coupling reaction, let's say I'm going to just keep the same simple organometallic. Most of the times when you do a coupling reaction, right, you do it with an organometallic and an alkyl halide. Some organometallic and an alkyl halide. And what ends up happening is in these coupling reactions, you make new carbon-carbon bonds, right? You're going to make a new carbon-carbon bond. So if you look right here, right, this part of the organometallic is the organic part. That's the part that does your coupling. So that's your nucleophile. And then over here, it's going to actually displace the leaving group. Right, so that's where the coupling comes in at. So you're going to put these two parts together. You're going to put the carbon here and the ring here are going to couple. And so when I do this reaction, I end up with this. All right, so that's my product where I made, this is my new carbon-carbon bond right here. It's actually a very powerful transformation for making carbon-carbon single bonds. All right. Any questions about that? The way that I like to teach it is like this in a very generic sense. I always do Cm plus Rx. And then on the other side, you end up with Cr plus MX, right? Because the goal is to couple whatever the organo part is here with the organic part here. So you want those two things to couple.
Dr. Russell, does the reaction happen in a concerted fashion? Is that where that coupling comes
This
from?
one, yes. Yes, it does. It's more than likely, this particular reaction more than likely is concerted, like a SN2 type reaction. It's a substitution.
Okay.
Yeah. Good question. Excellent question. All right. Any other questions about that? So that's an example of a coupling, and we're going to talk more about that later. And then let me give you an example of a Carbonyl Edition. So let me just scroll up. Is anybody still writing that before I scroll up? I don't want to rush it. I mean, I know we're virtual, but you're still taking notes and stuff like that. So
I'm gonna post it, so it's okay. Right.
all right. All right, so let's go to, let me show you an example of a Carbonyl Edition. That's a bad color. All right, so we could take that same organometallic. We take the same one, and we're going to react it with this aldehyde. All right, if you react it with an aldehyde, let me show you. We're going to talk about the mechanism and all that stuff later, so don't panic. All right, what you get out is, and actually this has to happen in 2 phases. So I'm gonna write out the intermediate first. So you get this. I'm gonna change the color on this CH3 over here just to make the point. Right? You get that. And then the magnesium ends up here. MgBr, and that's positive.
Is space in the back, or is it?
No, there's no stereochemistry. Let me just write it out. I need to zoom in so I don't have to try to compress it. So that's positive. That's oxygen is negative. And then up here I had this HCMG.
Oh, it's attached to the oxygen.
That's ionic. It's not covalent, because you know oxygen has 3 lone pairs around it, so it's negative. And then the magnesium. Let me move that back some. The magnesium is here, like a salt, kind of like sodium chloride or sodium bromide or a salt like that, right? So that's positive, that's negative. And then that's this, you get this intermediate every time you do one of those reactions. It's called a tetrahedral intermediate. Right, that's common. That's a common intermediate for these Carbonyl additions. Put a line here.
Dr. Russell,
Yes.
what's the main difference we should know between the two?
The 2 reactions?
Yeah, carbonyl addition and coupling reaction.
Well, the Carbonyl addition is exactly what it says. You're adding a organometallic to a carbonyl. Coupling reaction, you're adding it to an alcoholide.
Okay.
You following that? So that's a big difference. That's 2 totally different substrates. Right? So this intermediate, we just quench it. We dump in some acid, and then we get an alcohol out.
Is the magnesium bromide attached to the oxygen or to the?
Yeah, it's positive. Okay. Oxygen is negative, so they make a salt.
Okay.
All right. So then you have this, and then this CH3 is here, and then I'm gonna change that color back to red just to make sure you get the point. And then this CH3 is here, right? So one of the outcomes of Carbonyl Edition is the formation of alcohol. So you can use the organometallic reacted with a carbonyl to make alcohols, right? That's one of your key products from these types of reactions. I'm going to abbreviate organometallic as OM.
Are alcohol the only thing that can result from it?
Well, you can get a ketone, but I don't want to talk about that reaction just yet. Because if I do, I gotta go into the mechanism. And I'd rather just give you the example, and then when we get to that, we'll talk about it. You can also make ketones, but you don't start with an aldehyde, you start with an ester, right? So your start material is gonna be different. Here I reacted this with an aldehyde. Can you see that? So I got my organometallic here, and then I'm reacting with an aldehyde. Right, if I take the organometallic plus an aldehyde or a ketone, that's when we get alcohols. If I react it with an ester, then it's different, right? Because I can get a ketone or an alcohol, but I'll talk about that later. But that's a good thing to remember right here. That ketones or aldehydes. I got a mnemonic for this, but I'll let you see it when you watch the video. Plus organometallics will give alcohols, right? So ketone aldehyde will give you an alcohol, and then if you use an ester, you're going to get a ketone as the product, unless you use more than one equivalent of the ester. But I'll talk about that later. I don't want to talk about that now because I just wanted to give you these examples to kind of chew on.
Excuse me.
Mhm.
What
Go back down.
happens to the magnesium bromide in this?
Good question. So you see right here how we use the acid. So that's just H plus. Let me fix that plus. It looks like I'm trying to put Jesus back on the cross. So you see how that's H plus, right? So whatever the counter ion is to that, it doesn't. So let's just say we use, I'm going to go ahead and do this. Let's say we use HCl.
Mm-hmm.
You following that?
Yes, sir.
So when I quench this with HCl, obviously the H plus is going to end up here, right, on the oxygen. And then the chlorine is going to end up with MgBr. Like that.
Mm-hmm.
So this part of the salt ends up with whatever the conjugate base is of your acid. So whatever acid you use, once it gives up H plus, the conjugate base that's left, that's going to find magnesium, and they're going to get together and make a salt.
So basically, since you only had H plus initially, MgBr just is like floating away by
Yeah,
itself.
I just did show it's actually not floating away, but I just didn't show the other part. It's always going to combine with the conjugate base of your acid. Yeah, I should have shown that here in the example because that's a great question.
But I'm saying for initially, since you only had H by itself minus the chlorine.
But even if I have H by itself, it's always going to be connected to something.
Oh, okay.
H plus is just a way to indicate that you're using an acid. So if I just write H plus, that means it could be any generic acid, any acid, right?
Oh, okay.
But every acid has a conjugate base or counter ion with it. So whatever H plus is attached to, that's going to end up with magnesium in this case. That's a great question, though. That's good thinking. All right, any questions? Any other questions? All right, so let's look at some ways to make these organometallics, and then we're gonna come back to how we use them. We're gonna come back to the coupling reactions. We're gonna do a lot of practice with that, and we'll come back to those carbonyl additions. So let's go and talk about synthesis of organometallics. All right, so the first, I'm gonna show you the organometallics first, and then I'm gonna show you how to make them. All right, so the first organometallic is here. I'm just gonna do the same one I already showed you. And this is called a Grignard reagent. Right, it's called a Grignard reagent. The key is that it has a covalent bond between carbon and magnesium. That's how you tell it apart from other organometallics. So we're only going to talk about these two and how they react. So you have Grignards, and then you also have, let me write this out. So I'm gonna just write it out like this. This is what's called a Gilman reagent. It's also, you'll sometimes see it referred to as a cuprate. All right, so Grignard reagent is carbon magnesium. Gilman reagent is carbon copper.
Oh, it's copper.
Oh, wait, that's CuLi?
Yeah, it's copper, and then let me zoom in because I want to show you something. I'm glad you said that. So I'm gonna erase the lithium. It's actually copper, Cu, but that copper has a long pair of electrons on it, and it actually has a negative charge. So it's a salt with lithium, right? But when you see it written out, you won't see the electrons or the charges. So it's normally written out as this CuLi. It's understood that lithium is positive and carbon is negative. Right, and then that copper is always going to have two groups attached to it. So sometimes you'll see it written out like that, R2CuLi. All right, any other questions about anything?
I do. The first reagent, the Grignard reagent, is that Grignard? Is that similar to what we just did?
Yeah, it's the same one.
Okay.
I didn't give it a name at the time.
Okay.
Yeah, just the G, the middle G is silent, so just it's like Grignard. The G, the G and the N go together.
Oh, it's Grignard.
Grignard.
Grig.
Okay.
So think about it like, let me give you the phonetic spelling, the social media spelling. So Gran, and then yard. So that's how you pronounce it, Grignard.
Okay.
The G, I put a G-R-Y-N, even though my G looks like a 6. The mark of the beast. So it's a Grignard. So that middle G, that G and N go together. All right. Uh-oh.
Gotcha.
All right, so Grignard is with magnesium, and Gilman is with copper. Those are the two organometallics that we're going to study. There's a bunch of them though. Don't think it's just limited to these two. You have what's called Suzuki coupling that you can do that uses like, I think it's platinum, and then Stille coupling that uses tin. So it's a whole bunch of different, it's a long list of organometallic reagents that you can use. And most of the time they're used to make carbon bonds, all right?
What's the word cuprate you wrote at the bottom?
Cuprate.
Cuprate?
So just pronounce it like this.
Is that just another name for the Gilman reagent?
Yes.
Okay.
Sometimes you'll see it called a cuprate, or there's one other name for it. It slips my mind, but there's one other name for it as well.
Okay.
Oh, it's organocopper. So you can call it a cuprate, organocopper species, or Gilman. But I like Gilman because it's simple.
Mm-hmm. And these are just other two ways of synthesis or of organometallics?
Yeah, well, these are the two organometallics that we're going to be talking about. We're getting ready to talk about how they're made now.
Okay, and then
Time is left.
for the other two we just talked about, that's just what
they do. So these are just some examples of how you use organometallics.
Okay.
So we started out talking about what it is. It's a carbon metal or covalent bond, right? With the carbon as the nucleophile. And then some of the things that they're used for, coupling reactions, and then Carbonyl additions, which I gave you examples of each.
Mm-hmm.
And now we're talking about the different types of organometallics, which we're only going to highlight two, right? The Grignard and the Gilman. And now I'm going to show you how to make both of them.
Okay.
All right. Any other questions? That's a great question, by the way. It's one of the things. I'm going to tell you something about organic that's different from GChem. Organic is like Lego blocks, right? So the best way to prepare and approach this class, prepare for and approach the class, is to always think about the big picture and then the little pictures that make it up, right? So the first thing we said was we're going to talk about applications and synthesis of organometallics. So that's the big picture. Then we start talking about what is an organometallic, what do you use them for, and then how do you make them. So all those little subtopics come under that big umbrella. So if you can remember how to organize the information, I promise you it won't be as bad as people have told you it is, because everybody hates organic. But it's just all about learning how to organize the information and when to use it. GChem is mostly just math, right? You got an equation, you apply it. You got an equation for this, then you apply it. But organic is more conceptual. So you got to learn how to compartmentalize the topics. That's why I always give you the image of an umbrella. So we got an umbrella that we're working under organometallics. So we're going to talk about some different topics related to that. So let's talk about that. How do you make Grignard reagents? Screen. I need to clean my screen. My finger is sticking to it. So how do you make Grignards, right? That's the topic now, right? And they're really easy to make. I'm gonna stick with the one we already have seen, but I'm gonna show you that you can make other types too. And you do it the same way, but just maybe the mechanism may be different, right? So I'm gonna take methyl iodide, and I'm going to react that with magnesium. And that magnesium, is a group 2 metal, right? So it's got two valence electrons. All right. So what happens is the magnesium, this is not a chain reaction, right? Let me just show you the product first. So you get this covalent bond here between carbon and magnesium, and then magnesium is also a salt with iodine. All right, so all right, so let's look at what happens, how it happens. Right, so you got this carbon iodine covalent bond here, and what magnesium does is it basically donates one of its electrons, right, and facilitates that a homolytic cleavage of that carbon iodine bond. Right. So what should I get from that?
Did you get a radical?
You get a radical. You get a carbon radical. So carbon with 1 electron plus iodine, like so, right?
Mm-hmm.
Plus magnesium with 1 electron. Right? And so now the magnesium and the carbon can form a covalent bond. With that 1 electron that's left on magnesium. Right? And now magnesium is positive, and then the iodine over here is negative. Let me make that clear up here too. So the iodine actually has 1, 2, 3, 4, 5, 6. It's got 3 long pairs around it already. So when it comes off, after the donation of the electron for magnesium, that's why it has 4 long pairs around it here. Because it took 1 from the bond and then 1 came to it from magnesium.
Oh, okay.
All right. So that's how. So when you want to make a granular, and let me put this over here too. I apologize for not putting this in already. But you have to do this at really low temperature, and you have to do this in something like a ether, like a really what we call a Protic solvent. Right? Aprotic means no H plus. Right? No H plus can be present, period. Because if you have any H plus in here, I'm gonna change this. Any H plus is just gonna protonate that methyl group. So you're gonna end up with CH4 plus MgI, right? This is bad. Right? So no H plus. That's why you gotta use a solvent like ether or aprotic solvent so that you don't get that protonation. That will screw you up. I had a friend in graduate school. I tell this story every time I teach this. I have a friend in graduate school who was trying to make a Grignard, and it kept failing. And what he figured out was that the flask, maybe I can illustrate this. So he had this thing on top of the flask called a cold finger, right? And it's connected to this round bottom flask like this. But there was a gap in here. And since you're doing it at low temperature and like this real -78 ice bath, right? There's a lot of condensation because the room is room temperature, and then you got this -78 ice bath going. It's actually dry ice and acetone. but there was a lot of condensation around the cold finger, so all this water is dripping down, and that was a gap between the flask and the cold finger joint. So water kept getting in. It took him a week to figure out what he needed to do. So finally, he just wrapped everything in electrical tape, and it worked because no water could get in. But if any protons get into a granular, it's just going to get protonated because that carbon is very nucleophilic. So any H plus, you're done. So you got to use a aprotic solvent, right? A solvent that has no H plus, right? And then you can do the reaction. And you got to do it at very low temperature because it's a highly exothermic reaction. All right, any questions about that?
Not right now.
Hmm?
I said not right now.
Okay, if questions come up, ask them. You know, I hate lecturing. I like discussing. So if you have a question, just go ahead.
I know you mentioned the Protic Solvent.
Mm-hmm.
What's that over there? Wait, that's highlighted on top of the H plus.
No.
Oh, okay. Oh, that's right. You said no, H plus.
I'll write it right here. I'll write a capital N. So no H plus can be present. Period. It'll ruin your granular. You want to spin your wheels for a week? Make a granular in a solvent that has protons in it. Let's see your time. It'll never happen. All right.
So I just want to make sure. So the main topic, like the first topic is synthesis of, overall of everything. What synthesis of organometallics?
Yes.
Okay.
All right. So granules you make by stirring, again, an alcohol halide with magnesium metal and -78 in an aprotic solvent. So alcohol halide, you can see that here. You got your alcohol halide, you have your magnesium metal at low temperature, -78 in an aprotic solvent. So it can be ether, THF, benzene, toluene, it doesn't matter, but it's got to be aprotic. All right. Any questions about the granule or how to make it? I'm not necessarily gonna ask you for the mechanism, but I just wanted to show you how it happened. Right. And a granule, somebody tell me again what a granule is. How do you distinguish it?
It's going to be a covalent bond between the carbon and magnesium.
Good. Carbon and magnesium covalent bond. That's the distinguishing property of it. Now you might think that the granule it's a simple reagent, but it's actually, you can make lots of different types. It's actually very versatile.
Dr. Russell, could you slide the screen up for a second, please?
Slide it up.
Yes, sir.
Back to
Yes,
you.
sir. Yes, sir. I just need to see that CH4.
Oh, yeah, okay. Make sure you
All right,
write down
thank you.
bad. Don't leave that out. And the exclamation points. All three.
Yes, sir.
All right. Got it?
Thank you. Yes, sir.
All right. So let's look at some other types of substrates that you can make granules. So if I take magnesium and I react it with a benzene ring, right? We'll call this, like we said, we can use alcohol halides. We can also use aerial. Let me zoom in on that because I'm struggling trying to. Right, we can use what's called an aero halide or aromatic halide. And if I do that, that's going to give me this granule right here. Right? Very high yielding reaction too. But the difference is the mechanism is probably a little different here. It probably doesn't go through a radical because of that sp2 carbon. Probably goes through a different type of mechanism. Maybe some type of insertion. I'm not even certain about what mechanism this goes through. All right, again, you're doing this at low temperature, so minus 78, and then degrees Celsius. And you're doing it in ether or some other aprotic solvent. So you can make an aerial granular, or you can make a hold up. There we go, sorry. Or you can make a vinyl granular. If you take magnesium and a vinyl halide. I'm going to say iodine again. I'm using iodine for a reason. I'll tell you in a second. Minus 78 in ether, and you're going to get a vinyl granular. Right? Very, very versatile reaction. And being able to make these types of substrates makes it even more versatile, because now your coupling reactions become more diverse. Right? You're not just putting two alkyl chains together. You can put aromatic rings in place. You can put vinyl groups in place, and that makes the reactivity of your substrates even greater, right? Because the vinyl group is a functional group that can be further functionalized. So is the arrow group. So all of these things make this a really versatile reagent. A lot of stuff you can do with it. And let me give this a name down here too. Uh-oh, not that. This is a vinyl halide. And this is an aerial granular. And then this will be a vinyl granular. All right. Very, very, very versatile substrates. Any questions on any of that?
Yes, sir.
Go ahead.
You were going to tell us why you used iodine?
Oh yeah. So when you make a granular, your best substrates are halides. So you can use let me just do this. This will be another topic. Halide reactivity. So if you have an alkyl halide, I'm just going to use X. Aerial halide or vinyl halide, right? Iodine, and then let me do this. Iodine is more reactive than bromine, which is more reactive than chlorine. Fluorine does not react. Right? The reason is because iodine is larger. Right? So iodine is bigger. So let me just illustrate that. I'll come back to that in a second. So if I had an iodine here, right? The bond here, because iodine is larger, the bond is longer and weaker, and it's easier to break. So that's why that's why iodine is preferred. Now you can use bromine or you can use chlorine, but iodine it'll react faster. Right, the larger the atomic radius, the longer that bond is going to be, because that atom it doesn't want to sit right on top of carbon. All right. Any questions about that? So iodine is going to be alkyl iodide, or aryl iodide, or vinyl iodide is going to be more reactive than any of your other halogens, because again, the iodine bond is just easier to break. All right. Any questions about that?
No, sir.
All right. I'm gonna take 3 minutes and talk about cuprates. They're not as well. Let me take that back. Let me not compare them. Both of them are about the same. So let me just take 3 minutes and talk about that. Then I'll stop. Then we'll talk more about it on Wednesday. So a cuprate again is an organocopper. Compound, right? In the basic structure, you have a copper. You have 2 groups attached to that copper. And then that copper also is a salt with lithium. All right. So the way you can see that there's a lithium involved here. So the way you make this, I'm gonna show you that, and then we're gonna stop. Right. So you have to have right, in the synthesis of the cuprate, you have to start with what's called a organolithium. Right, so you have this organolithium precursor. So the way you make that, very simple. You kind of make it just like you make a Grignard, right? You take, I'm going to use this, butyl iodide. So butyl iodide plus lithium salt, right? And you're going to need 2 of those. 2 moles of lithium salt, 1 mole of lithium, 1 mole of butyl iodide. That's the stoichiometry for the reaction. Right? When you react those together, you're going to get this organometallic or organolithium plus lithium iodide. All right, questions? And this is what you're going to react with copper to make your Yeoman reagent.
Wait, why'd you write the numbers on top again?
Yeah, so that's just the ratio. So it's 2 parts lithium and 1 part alcohol halide. So so once the lithium is covalently bound to copper, you still have 1 left, and that makes a salt with the leftover iodine.
Oh, okay, that's why it's lithium iodine.
Can you see it right here? So you got a lithium right. Uh-oh, I hit the erase button instead of the highlighter. You got a lithium right here and 1 right here.
Mm-hmm.
So that accounts for your 2 lithiums.
Okay.
All right. So once you make that, I'm gonna show you, write the reaction out. Now you're gonna add copper iodide, and you're gonna take 2 of those. So 2 of your alkyl lithiums plus copper iodide, right? And then when you react those 2 together, that's how you get a Grignard. I'm sorry, a Gilman. My bad. I want you to pay close attention to this. So you're gonna have 2 of those chains, because you got two of them here. You're gonna have two chains. Never mind. And then copper, lithium. Again, copper is gonna be negative. Lithium is positive. Plus, the second lithium is gonna end up with iodine. Right?
Okay.
And this is also done at low temperature. And in an aprotic solvent, like ether. This phone rang one more time. Slap somebody. All right, y'all ain't hear that part. I'm gonna edit that out. Actually, I'm not. Maybe it'll be a deterrent to people calling me during class. All right. Any questions about the Gilman?
I do have a question.
Go ahead.
In the beginning, when the lithium or
When you're making the alcohol.
when the iodine is leaving as a leaving group, is it going to leave as like a radical, or is it going to make the carbon positive?
It probably is a radical because lithium has one electron, so it's a great one electron donor.
Yeah.
So it probably will leave as a radical. That's a good. Okay, the mechanism is probably very similar to making a Grignard, where you donate that one electron from lithium to iodine, you break the bond. You follow what I'm saying? And then come in with.
Yeah, I was just confused because I knew that if iodine left and made it positive, then lithium's also positive. So I was like, why would they?
No, that's not going to work, right? Yeah. That's a great observation. It probably follows a similar type mechanism to the Grignard.
Okay.
Because all those metals over there, like sodium, lithium, magnesium, all those group 1 and group 2 metals, they're great one electron donors. So more than likely, this alkyl lithium synthesis probably happens almost identical to the Grignard synthesis.
I have a question.
Go ahead.
For the last step, after now that we're adding the copper iodine, why do we use the 2 of that carbon lithium?
So 2 of the alkyl lithiums?
Yeah, thank you, alkyl lithiums.
So what you're trying to do with the copper is, since it's a transition metal, it likes to have a certain number of valence electrons. So if you only add 1 of those, when you get to the product, right, what happens is, let me show you. So when you get to the product, if you only add 1, you got this Cu I, right? This is not reactive. Right? It's not reactive. So it doesn't become reactive until I add that second alkyl lithium and make that carbon negatively charged. Okay. Then it can act as a nucleophile when you react it with another, either alkyl halide or carbonyl compound or some other electrophile. But by itself, like right here, is not reactive. Great question. That's the first time anybody ever asked me that.
Also, what is the because you were talking about how it has to be extremely low temperatures because it's a highly exothermic reaction. But so then, what's the impact if the temperatures are any higher?
Well, depending on what concentration you're working at, you're talking about maybe a potential explosion or the reaction. I don't know how to put this, but the reaction vessel basically overflowing, like if any gases are released or anything like that. So you just have to be careful. Now, most of the time, though, you're working at small, low concentrations. But if you scale this up to like a gram scale, then you got problems. But it's best to do it at low temperature, because once the temperatures increase, also your star material start to decompose, because this copper species right here is very reactive, right? So you want to keep it at low temperature to keep the energy down, so it's more selective in what it reacts with.
Okay, thank you.
Yeah. All right.
That copper lithium the same of the copper lithium above. You just don't use the bonds. You don't show the bond or the chain. I mean, you don't show the chain.
You mean up here?
No, I'm saying that carbon lithium molecule is the same as the initial equation. You just don't show the chain behind it.
No, no. This is what you start with to get to here. So you take 2 of these plus copper iodide, and that gives you the cuprate. Is that what you're asking?
Yeah, so that cuprate right there with the chain, that's the same as the cuprate that we initially got with the 2 R's.
Yes. You mean up here?
Yes, that's what I was asking.
The chains are actually the R groups.
Okay, yeah.
Yeah. This is just a generic way of showing it. Right? But again, just like a Grignard, I can use different types of organolithium species, and it'll, right? I can have an aerolithium or a vinyl lithium, and if I react those with copper iodide, I'm going to get the 2 groups will be the 2 aero groups or the 2 vinyl groups. It just, both of those work just fine.
Okay.
Just like the alkyl groups would work. We'll talk more about it because I know we're out of time. We can discuss it on Wednesday. And then there's a handout on Blackboard. Let me do that before we log out. Let me stop recording too.